Welcome to today's explainer. Right now there is a massive, practically invisible engineering problem happening directly above our heads and right under our feet. Today, we are going to explore the hidden engineering magic that's absolutely crucial to keeping our modern, rapidly changing power grid from completely collapsing.
To really grasp why this magic is suddenly so critical, we have to look at the sheer scale of the renewable boom. According to the U.S. Energy Information Administration, an astounding 94% of all new utility-scale electric generating capacity added to the U.S. grid in 2024 is expected to come from just three sources: solar, wind, and battery storage. Think about that. This isn't just a gradual shift anymore. It's a fundamental, rapid overhaul of how we generate power.
Okay, let's dive into this. Here's our roadmap for today's explainer. We'll start with the renewable energy boom, then look at our changing power grid, dive into the hidden mechanical problem with followers, enter the ultimate technological solution, grid-forming inverters, and finally wrap up with some real-world grid success. Let's get right into it.
Number 1. The renewable energy boom. Why exactly is this happening so incredibly fast?
Well, the answer is beautifully simple. It's economics. If you look at Lazard's levelized cost of energy analysis, it reveals this dramatic downward curve over the last decade. The cost of utility-scale solar has plummeted by 83%, and the cost of onshore wind has dropped by 63%. So these technologies are booming because they are, quite simply, the most cost-competitive forms of new electricity available today. It just makes financial sense.
Moving on to part 2, a changing power grid. We're going from heavy metal to digital.
Because we're building out so much wind, solar, and battery storage, we really need to define a critical term that you'll see all over power systems engineering today, and that is inverter-based resources, or IBRs. Whether you're looking at a solar panel, a giant wind turbine, or a massive battery container, all of these booming new technologies fall into this one digital category. See, unlike traditional power plants, they don't produce alternating current naturally. They produce direct current or varied current, and they completely rely on digital power electronics, which are called inverters, to convert and push that electricity onto the grid.
And this brilliantly illustrates the contrast. Think about the old way versus the new reality. On one side, you've got conventional, heavy, rotating synchronous generators driven by coal, natural gas, nuclear, or hydro. These physical behemoths have massive momentum. They literally spin at the exact frequency of the grid. But on the other side, we have the new reality. Solar panels and batteries connected to a static, digital box on the wall. There's no heavy spinning metal. There is absolutely no physical momentum. It is entirely digital.
Which brings us to part 3, the problem with followers, or losing the heartbeat.
This is where things get a bit serious. As we replace those massive spinning turbines with static digital boxes, our grid is literally losing its physical heartbeat. And that poses a pivotal, honestly, potentially catastrophic question for power engineers. If everyone on the power grid is programmed to be a follower, who sets the pace? Because historically, those heavy spinning generators acted as the grid's pacemaker.
The big problem we're facing is that our standard inverters are essentially mindless followers. They're known as grid-following inverters, or GFL. They only control their output current, and crucially, they are completely dependent on another source to synchronize to. They literally just wait to measure the voltage and frequency from older spinning generators, and then they tag along like backup dancers without a lead singer. They cannot make their own voltage waveform. So if a major disturbance happens and the frequency drops, these followers can't fix it. They'll just happily follow the grid right down into a blackout.
But don't worry, here comes part 4. Enter grid-forming inverters, the digital leaders.
Now, what's really interesting about this dynamic is how perfectly researchers have captured it. Think of the old grid-following inverters as a group of followers, just blindly stepping in line together. But the new technology, grid-forming inverters, or GFM, they act as an independent leader, confidently stepping forward to set the pace.
Let's contrast these two directly, because it's a real game changer. While the dependent grid-following inverter only controls current, the new grid-forming inverter actually controls the output voltage. It doesn't sit around waiting for a signal from a spinning piece of heavy metal miles away. It can independently generate its own voltage waveform. It acts as a digital pacemaker, instantly injecting stability into the grid the very millisecond a disturbance occurs. It is exactly the digital leader our new renewable grid desperately needs.
And the crazy thing is, the industry has literally had to scramble to rewrite the rulebook to catch up with this. Look at the timeline. Back in 2003, engineering standards strictly forbade these inverters from leading.
The rules stated they shall not regulate voltage, period. But by 2018, as renewables really started to boom, they totally reversed course, updating the standards to say inverters shall regulate voltage. And now, moving into 2024, the Unify Consortium is publishing advanced version 2 specifications to standardize exactly how these digital leaders must behave. It's a complete 180.
Finally, Part 5, Real-World Grid Success. Because yes, it's already happening out there.
So the crucial point is that this isn't just theoretical software in a lab somewhere. On the island of Kauai, the local grid operator is successfully operating their grid at up to 90% inverter-based resources at peak times. They're achieving this incredible stability without heavy spinning metal by relying on multiple grid-forming battery systems running in parallel. The digital leaders are successfully running the island right now.
And we know for sure this logic scales up to massive, interconnected systems as well. Just take the Texas ERCOT grid. In March of 2024, they hit a staggering new record of 75.67% renewable penetration. At that exact moment, they were seamlessly managing over 34,000 megawatts of variable power. To put that into perspective, that's enough to power millions of homes simultaneously, entirely managed by these new systems.
So what you should really take away from this explainer is that you don't actually need every single solar panel or battery to be a leader. Studies show that having just 25 to 30% of the system comprised of these grid-forming resources, especially when you pair them with energy storage, unlocks an incredibly resilient future. It provides essential reliability services, the ability to black start the grid, which basically means rebooting the entire system from total darkness without any external power, and ultimately, it enables an infrastructure with ultra-high levels of clean, cheap, renewable energy.
The way we generate power has forever changed. The heavy, spinning metal that served as the heartbeat of our infrastructure for a century is fading away, and it's being replaced by silent, static, digital inverters. The technology absolutely exists to safely guide us through this transition, but it requires a massive, hidden digital upgrade in the wires above our heads. So I leave you with this to ponder. As this boom continues to spread like wildfire, is your local power grid actively preparing to follow these new digital leaders? Thank you so much for joining me for this explainer. Keep learning, and I'll catch you on the next one.